Okay, good. People are joining.
Thanks, Roderick.
You're welcome.
Are you able to make Stuart the host when he joins in?
I don't need to make him the host. I'm just setting it up now so that he can share his screen.
Perfect.
Who can share? All participants. So basically anyone can share, which of course could cause chaos if we all started doing it, but as long as only Stuart does it. I'm not actually sure how I switch hosts, but I know how to set it up so that other people can share their screens. So I'm sure switching host is quite easy, but in fact, let me have a look. Oh yeah, okay, it's easy to make someone else the host. Yeah. It's, you just go to their name and then say make host. Yeah, okay. But anyway, I've set it up so that anyone can share their screen, so it should be fine for Stuart. Sharing options. Okay, so I'm actually going to change this back to host only, and I'll make Stuart the host when he's ready. That's probably the safer way to do it. So once he's joined, I can make him the host. Gihan, I copied you in the message, but I've contacted ICT to sort out why the website's blocked from
I saw that.
which is utterly
that's unexplainable.
Yeah, I mean that's been a bit overcautious, I would say, to block the the society websites, unless you've got some stuff on there that shouldn't be viewed in work.
I'd be interested to know because I'm the administrator there.
Still no Stuart.
Yes, I'm pushing.
I'll send him an email directly. Actually, let me.
His contacts.
Oh, okay. Yeah, I don't have his phone.
You sent him a link, Roderick?
Just sent him a link again. He should have got it from you, but I've just sent him an email directly with the link. I don't have it. The quickest way I have to contact him is email. I don't have his phone number. Come outside, Evan. It's disappeared. Okay, he's here. Let me make him the host. Okay, Stuart, you are now the host, so you can share your screen.
Thank you very much.
Okay.
Yes, so to other participants, they have the new link.
Greetings. You know, that is my worry.
You can
Because
see.
we have
We can see.
we have sent the link to a lot of people.
Yeah,
Because we have the AGM. Start now. You need to make the introductions.
More people are joining now, so
Oh, me.
Yes, please.
Oh, yeah. Are we starting now?
Yes, we are starting now.
Oh, that's not good. That's not good. Because a lot of people haven't received the new link.
We have to start now because the AGM is at 7:30.
Yes. But
Monitanya, I think we can hear you. Just introduce the speaker and then the others will join.
oh, all right. All right. Thank you very much. Let me welcome those who have been able to be present, and today we have a talk from Mr. Stuart Marongwe. Mr. Stuart Marongwe has obtained his licentiate degree in physics from the university in Cuba, and he went on to pursue his master's degree at BUST, working on quantum gravity. And he is currently pursuing his PhD still at BUST, which according to me, I feel it was a bit unnecessary, because you know, looking at his report, or the report from the reviewers of his MSc, and also looking at his MSc, and also the papers that he has published so far, and also that came out from his MSc dissertation. The work is worthy of a PhD. So I think there it is just a formality. And what I'm saying is not my personal opinion alone, as I alluded. it is also the opinion of the reviewers who examined his dissertation. Now, if you are ready, Mr. Marongwe.
Yes, good evening, Dr. Mutsi.
You may indulge us.
Yes. Thank you very much for that introduction. I would also want to thank the Astronomical Society of Botswana for hosting me on their platform. Tonight's talk is about horizon scale tests of quantum gravity using the Event Horizon Telescope observations. So in this talk, I'm going to compare two interpretations of gravity. One is an interpretation, a geometric interpretation championed by general relativity, and the other is a quantum interpretation modeled by the nexus paradigm of quantum gravity. So join me tonight as we explore the frontiers of physics, find the nature of gravity and its origin. So in order for us to understand to have a complete understanding of gravity, we need to be able to answer three fundamental questions. That is, what is gravity? How does it work? And why does it work? Now, all of us are familiar with gravity. Gravity is the most familiar force, but yet the most mysterious.
Let me
keeps the
disturb
moon
you a
in
bit.
orbit about the Earth, the planets about
May
the
I
sun,
disturb you a bit?
makes apples fall, and keeps you and me on the ground.
Mr. Speaker, can you wait while we ask others to close their mics?
Yes,
Okay.
yes. Yes, please mute your microphone so that we can hear nicely. Thank you very much.
All right, is that okay?
Yeah, that's much better. Stuart, there is a way for you as speaker once you start to mute everyone's mic, so you may want to do that once you start.
All right. All right, let's proceed with our talk. As I was saying today, tonight's talk is, I'm going to distinguish between the geometric interpretation of gravity and the quantum interpretation of gravity. So this involves fundamental physics. So we are going to be exploring the frontiers of physics. All right, I can't disable the other people's mics. Gravity, can everyone hear me? Gravity is the most familiar force, but yet the most mysterious. It keeps the moon in orbit about the Earth, the planets about the sun, makes apples fall, and keeps you and me with our feet on the ground. Like I was saying, we need to answer three fundamental questions. One of the first questions to answer the what part of gravity, or what is gravity, was the polymath, the English polymath, Sir Isaac Newton. Sir Isaac Newton analyzed the phenomenon of gravity, and he's the first one to coin the term gravity from Latin. Sir Isaac came to the following conclusion after analyzing Johannes Kepler's laws of planetary motion. Now, Johannes Kepler was a German astronomer who came up with some laws of planetary motion, which he established from Tycho Brahe, his mentor. So he came up with laws that govern how planets in the heavens are moving. And so Sir Isaac Newton analyzed these laws and came up with this observation that it is as if there is a force of attraction between two bodies, which is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. So Sir Isaac Newton is attributing a quality of a force to gravity. He perceives gravity as a force. And he summarizes this statement in his famous universal law of gravitation: F is equal to G mm over R squared. So the problem with Sir Isaac Newton is just trying to ask what part of gravity. He's not explaining the how and the why, but he manages to unify celestial and terrestrial mechanics. Celestial mechanics involves the motion of comets and planets, whereas terrestrial mechanics is about the motion of falling objects on Earth. So his success was to unify these motions by attributing the force of gravity as the same thing that is making the objects in space orbit the sun, and the same force that is causing the apples to fall on the Earth. So he unified, one of his major successes was to unify terrestrial and celestial mechanics. He also succeeded in explaining the laws of planetary motion that Kepler had earlier on established. And one of the major successes of Newton's universal law of gravitation was the discovery of the planet Neptune by Urbain Le Verrier. Urbain Le Verrier used Newton's laws of motion to predict the existence of planet Neptune due to its perturbations or disturbances on planet Uranus. So he managed to calculate and tell astronomers where to look for planet Neptune using only Newton's laws of motion. And this was one of its major successes. But then Newton's law had a problem. It could not account for what is known as the precession of Mercury's orbit. Now, the planet Mercury is close to the sun. As it orbits about the sun, its orbit moves along as well, as shown by the red arrow. Now, this motion of the orbit can be attributed to the other planets tugging on its orbit. But then there is some residual motion that is left that cannot be accounted in Newtonian gravity. So this posed a problem because the Newton's universal law of motion could no longer explain the heavenly motion. So a new interpretation of gravity was needed. And this interpretation was afforded by general relativity. So what is general relativity? This is Einstein's interpretation of gravity, a new way of interpreting gravity. Now, unlike Newton, Einstein is now trying to explain how gravity works. So general relativity interprets gravity as a manifestation of curvature or space-time. It can be considered as describing straight lines on a curved space-time manifold. What am I saying here? I'm saying object, if there was no massive object like the Earth, object would move in a straight line. But the presence of a very massive object like the Earth bends the space-time around it, such that the object that was moving in a straight line, such as the moon, will follow a curved path, although it's still moving in a straight line, but it's moving in a straight line in a curved space-time. So the moon ends up orbiting the Earth. So Einstein here has explained how gravity works. His explanation is that the energy density, like for example, the planet Earth, curves the geometry of the space-time around it. And he expresses his argument in this formulation. The left side of this equation shows the geometry. The right side shows the energy density. Now I'm including some equations in this talk because there are some students who are eager to know about how gravity works and they are curious about some equations. So of course, for those who are not interested in equations, you can see them as good works of art. But for the students, this is vital. This is vital for them to continue on their research on gravity. Now, general relativity had a lot of successes. Apart from explaining the precession of the orbit of planet Mercury, it managed to predict that as light passes through grazes the surface of the sun, it is bent, and he calculated the angle of how it will be bent, and this was observed by Sir Arthur Eddington, and that was one of the remarkable successes of general relativity. Another phenomenon predicted by general relativity is called gravitational lensing. Because light bends as it passes a massive object, it will form what is like a lens, a convex lens that we are familiar with usually in biology. So there's a gravitational lens which can be used to observe background stars, and it magnifies them. There's another phenomenon called the red shift and blue shift. This is caused by when light falls in a gravitational field, its frequency moves to a higher level, which means it has blue shifted. And if it's leaving the gravitational field, its frequency moves to a lower frequency, which means it has gone redder. There's another phenomenon called Shapiro delay, which means that when light passes through a massive object, it takes a longer path than when the object was not there. This has been confirmed using the Cassini probe that went through Saturn. It also predicts the existence of black holes. These are regions of space-time where gravity is so intense that light cannot escape that region. It also predicted gravitational waves that were detected in 2015, sorry. But general relativity has its problems. First of all, it cannot explain the dynamics of stars in galaxies. Now, one would expect that the stars in galaxies would follow the same laws of Kepler, just like the planets around the sun. So when we expect that, we see this dashed line. This is how we expect the stars orbiting a galaxy to behave. Just like Mercury will be faster, followed by Venus, followed by Earth, which becomes slower and slower as you go. But when it came to observing stars, especially by an astronomer named Vera Rubin and Ken Ford, they observed that the speed of the stars followed this line and even went higher, or they were all the same as they orbited further away from the galaxy. Now, the only way general relativity can try to explain this phenomenon is by postulating the existence of some hypothetical dark matter which has not been detected as yet. General relativity also cannot explain the existence of what is known as dark energy. Dark energy is considered a force or an energy that is causing the universe to expand faster and faster. So it's causing accelerated expansion. What the nature of this energy or force field is still mysterious, although general relativity can account for it using the cosmological constant, which Einstein had added earlier in 1917 to make the universe static. But it was observed in 1998 by some astronomers that that constant is necessary to explain the accelerated expansion of the universe, although the nature of that force is not known. Also, this from the onset, everyone knows that general relativity breaks down inside the black holes. The equations of general relativity reveal what's known as a singularity or an infinitely small point inside it, where the laws of physics break down and general relativity cannot explain it. A singularity, in other words, is a way of saying that the laws of physics, your theory has failed. It cannot explain what is taking place. So these are some of the problems that general relativity faces. But the biggest problem is that general relativity is not compatible with the principles of quantum field theory. We cannot have a universe which is described by classical theory, which is general relativity, and by quantum theory. Quantum theory obeys different principles than classical physics that started with Newton. It observes the uncertainty principles, which means if you make calculations in quantum mechanics, you make probabilities. You can say, if you give me this initial set of conditions, I can give you a probability what will come next. But in classical mechanics, you speak of certainty what will come next. So there are probabilities in what will happen in quantum mechanics. It also has some defined quantum states. It also has this thing called superposition of quantum states, where you can find a particle at multiple points at once. It also describes the universe in terms of wave functions, and it doesn't assume a curved space-time like general relativity. It operates on a flat space-time. Now, there have been attempts to quantize general relativity so that it obeys the laws of quantum mechanics using some standard formalism, but these yield meaningless values, infinite values. So it's difficult to quantize general relativity. Now, so we are in a crisis. We cannot reconcile classical mechanics of general relativity with quantum mechanics. But a crisis, as someone once said, generates ideas. So we need to generate ideas that explain this crisis. The solution is quantum gravity. So what is quantum gravity? It is a much sought after theory that explains gravity in the language of quantum field theory. So it's a theory that searches to explain Einstein's explanation in terms of the principles of quantum mechanics. So this quantum gravity is applicable in situations in which matter is both microscopic and massive. Now, if you say something is microscopic, which means you are speaking relative to a certain length scale. For example, a mountain sees an ant as microscopic, but a grain of sand will not see an ant as microscopic. So it's applicable when quantum gravity emerges, is because something is extremely tiny and dense relative to a certain scale. Now, these scales are called localities. Now let's look at this line. This line could represent a dimension in space. It could be length and or time. But this line, we are also taught this now as a number line in primary school. If you look at this number line, you will find that there's a missing digit here, 0. I will explain in a moment why that is missing. But the explanation with the interpretation we got from primary school was that these numbers are representing points in space. And that was the beginning of our geometric interpretation of the world. But now we need to make a different interpretation of the world. Instead of looking at this number line in terms of points, we should look at it in terms of locality. What is the locality? We look at this range between -1 and +1, and we call it a locality. So this will be the smallest locality in space. For those who study quantum gravity, the smallest locality is called the Planck length. So this is the smallest locality you can get in space. Now, once we make localities, there are other localities that are multiples of the smallest locality. So this number 2 locality is twice as long as the small locality, or twice as wide as the small locality. This one is 3 times as wide. It's not that these other larger localities are made up of the smallest. It's just that they are only twice or 3 times or 4 times larger than the smallest locality. So we now start thinking in terms of localities instead of points. Once we start thinking in terms of localities, we enter the quantum arena, because as we start following Heisenberg's uncertainty principle, we now become guided by Heisenberg's uncertainty principle, which says that the smaller the locality, the more energetic it is and the shorter lived it is. So according to Heisenberg, this is the smallest locality. It's very energetic, but it is also short-lived. Now, this locality, when it's short-lived, it decays into this longer locality. How does it do that? It emits the smallest amount of energy, and once it emits this small amount of energy, it expands, because its energy is lowered, is reduced, it expands. The next step, it releases the smallest amount again, and then it expands. So it goes on expanding. The smallest amount of energy here from my research is the Planck constant multiplied by the Hubble constant. Now, another interesting aspect from this onset, you will find that general relativity becomes unified. Why? Because these localities, what I'm calling localities, are also called compact Einstein manifolds. They behave this law. So these localities, I'm talking here without matter. Already, there seems to be appearing, gravity seems to be appearing in the absence of matter. So as we develop those compact Einstein manifolds, if I display them in 2 dimensions, they represent circles of this format. This is the smallest locality, the next larger locality, and so forth. The smallest locality is in the highest quantum state, or n, or the number associated with it is 10 to the power of 60. Each locality, for example, is also associated with a rotational speed, which is given by this formula. So this rotates, this next locality rotates faster than this one, followed by this one, and then this one. For a test particle, if I put a test particle that is, it has negligible gravity, you'll find that as it moves from this locality to the next locality, it needs a minimum acceleration in the universe of this formula, of this value. It's a very tiny acceleration to move from one locality to the next locality. So as it moves into a faster locality that is orbiting, that is rotating faster, as you can see. It follows a curved path as it moves from the tiniest locality to the largest locality. It follows a curved path on the other side. Now, as you can see, this phenomenon seems to be representing what is happening in spiral galaxies, okay? So what is happening in spiral galaxies? Why they seem to be obeying this quantum behavior like? It is because when we look at stars in a spiral galaxy compared to the locality we are comparing with, the star is a microscopic object which is also dense. The star is a microscopic object which is also dense. That's why it's now entered the realm of quantum gravity, which we described earlier as it's applicable when something is tiny and dense. So a galaxy observed from these scales, a star looks like a tiny dot, but we know that a star is massive, so it's a tiny dot which is dense. So the next paradigm is saying gravity is general relativity plus a contribution from the quantum vacuum. Now, if I just want to show you what was happening here, you could see as the dust particle was moving from high energy to low energy, it was flowing from a region of high energy density to a region of low energy density. This phenomenon is also known as Hubble flow. We could even consider galaxies as, if we zoom up at cosmic scales, galaxies become what? Tiny point-like particles that are dense. So they also succumb to the laws of quantum gravity. So you would see this pattern also happening with stars. So which means galaxies close to us, which are closer to us, are moving at a less speed than those that are further away from us. And those that are much further away move even faster and faster, obeying this same law. It's also called the Hubble flow. So in Nexus paradigm, this is the matter density. The contribution of gravity comes from matter density plus the vacuum. And this part is just showing the Einstein, compact Einstein manifolds that I was talking about. Now, for the students who are interested in the full quantum, this is called a semi-classical version. The full quantum version is this one. It's meant for the students who are interested in following this research. This part shows the flow of space-time. This part shows that a massive object acts like a sink. So in the Nexus paradigm, gravity is defined as the flow of space-time from a region of high energy density to a region of low energy density. You see, this massive object creates like a region of low vacuum energy density from a region of high high energy density. So when an apple is falling, it's not that it's being pulled by a force. It's because the space is flowing towards the earth. So an apple, a stone, a gold bar can fall at the same rate because they're like on a conveyor belt that is flowing towards the earth or accelerating towards the earth. Now, the other thing that quantum gravity also shows is that as objects get closer to a massive object, their location becomes fuzzy in compliance with Heisenberg's uncertainty principle. Using the semi-classical version, the Nexus paradigm can now explain the observed galaxy rotation curves. These are called galaxy rotation curves, or the behavior of stars at different distances from galaxies without the need of hypothetical dark matter. A very important critical point happens when this part at solar system scales is much more prevalent, dominant, because this constant is called Hubble's constant. It is a tiny figure which does not appear at solar system scales. So at solar system scales, we see Newton. But if the radius begins to go up to galactic scales, this radius is dividing this number and it becomes small, such that it now becomes compatible with these terms. You will find that there's a certain level where this term and this term cancel out. And that's when this behavior begins to begin to happen, where stars begin to follow this, the locality, the speed of each locality around them. As you can see, this locality is moving slower than this locality, and then this locality is moving faster. As you move, following that equation, V is equal to HR. But in extreme gravity, these are the compact Einstein manifolds that begin to manifest in extreme gravity. So the successes of the Nexus paradigm are that at solar system scales, it predicts what general relativity does. It has different predictions in strong gravity regimes and weak gravity regimes. It also explains dark energy and dark matter as different manifestations of quantum gravity. It also derives the equations of galactic and cosmic evolution. If you look at this equation, it can describe how a cosmos is behaving, the universe is behaving, as well as it shows that at some level, galaxies are expanding at cosmic times, at very long time scales. Galaxies are expanding. It also derives the evolving baronic-Tully-Fisher relationship. This part is called the baronic-Tully-Fisher relationship. It has been empirically observed by astronomers that galaxies, the stars in galaxies follow this law. But in the Nexus paradigm, it is derived from first principle. But it is derived with this term to show that as time goes on, the speed of stars in galaxies begins to move. So we can expect stars with, especially galaxies which have population 2 stars, to have faster rotational speed than galaxies with younger stars. And if you notice, for those who are good in maths, if I derive this, I get this. If I derive this, I get the acceleration. This is the accelerated expansion of the universe that is being caused by dark energy, where astronomers are puzzled by the nature of it. It's still quantum gravity. If you look on this side, it still obeys Hubble's laws. Now, let us now look at what the nexus paradigm of quantum gravity predicts about the locality around a black hole. So if we have a telescope that can look at a black hole, what do we expect to see? And these are the things that you need to test the nexus paradigm. You are expected to see an outer circle, this one, which is 4 times wider than the inner circle. The inner circle is the quantum number 1, and the next one is the quantum number 2. So this state is the lowest ground state of space-time itself. That's the inside of a black hole. It's in the ground state n equal to 1. The next level is n equal to 2. So then you are also, according to the calculations from the nexus paradigm, there is a zone of peak emission. This zone is emitting radiation. Then this radiation peaks at this point where matter from this orbital is transiting to this lower orbital. So it emits it as a peak emission here. And that calculation shows that its peak emission is at 52 microarc seconds for the black hole at the center of a galaxy called Sagittarius A star. And for the galaxy, for the black hole M87, in the galaxy Messier 87, the ring will be 40 microarc seconds. These black holes can be observed using what is known as the Event Horizon Telescope, which I'll describe later. So what am I saying? The outer circle is 4 times larger than the dark depression at the center, and that there's an emission zone at a certain value of this. General relativity, on the other hand, is predicting that there's what is known as a photon ring, a ring of light of this dimension, and a ring of light of this diameter for M87. Now, the most important difference you should note here is that in the nexus paradigm, this is just a peak of emission. It's not a photon ring. It's the peak of emission of the emission zone. Now, I have to explain a bit about what is a black hole shadow and how it arises. In general relativity, if you consider light coming from this direction towards the black hole, if light is within this region, it will all of it will fall into this black hole. But if it just grazes above this circle, it will turn back and come back. Also, I could do the reverse. If light is coming from this region, in order for it to escape this zone, it has to pass through this circle, okay? But the difference between general relativity and quantum gravity, modeled by the nexus paradigm, is that the mass behaves as if it's half the mass in general relativity. So this shadow will be half the size predicted by general relativity. And something interesting about the photon sphere, in the quantum gravity paradigm, this ring, the n equal to 1 ring, is what we call the most probable radius. And the photon ring is what we call an expectation value of that radius. Just for those who have studied atomic hydrogen, there's a Bohr radius, then there's an expectation radius for that Bohr radius. So here we have the most probable radius, and this is an expectation radius. So you will find that the shadow of the black hole is not a definite shadowed shape. It fluctuates. It fluctuates between this size and the most probable size, the expectation value size and the most probable size. Has this been observed? Yes, it has been observed for the black hole M87. The shadow has been morphing, becoming smaller and bigger. So this is how, here I'm just trying to illustrate how the shadow is formed in quantum gravity. It is an amplification of this locality around a black hole. So this black circle is the n equal to 1, and this is the shadow it casts as the light bends away from it. And this n equal to 2 As light bends away from it, it creates this larger shadow. So the size of this larger shadow, as you can see from this calculation, is 4 times wider than the inner circle. And the peak of emission happens between the n equal to 2 orbital and n equal to 1 orbit. And if you magnify it, it appears there. As the light leaves it, it is lensed to this size. So what is the Event Horizon Telescope? It's a global network of synchronized radio observatories that work in unison to observe radio sources around the black hole. So what is it? This is a Earth-sized telescope that looks at black holes not using light, but using radio waves. So it takes pictures using radio waves, but the pictures are not taken in the same way you would take your camera. They have to record signals coming from each and every station, and then synthesize that to come up with a synthetic image. So this was the image that they got from 2019 of M87. And this was the latest image that they got from this year. Now, this image was from data obtained in 2013, but it was released in 2018. It was 2 of possible images. That's why they did not announce that they have seen the black hole, because they synthesized the image. So one of the images looked like this, and the other was different from this one. But they all assumed that this one was the most probable at that time. So they did not announce that they've observed the black hole at the center of our galaxy. So this also looks like a long photo exposure, but this one is more or less like a snapshot. Now, let's look at what is happening, at how now the general relativity and the quantum interpretation fare out on these observations. So if we take the image of M87 and we make a cross section of it and look at this light around it from a profile point of view, like we have cut a slice like a cake and start looking at the side view, we'll see this part here is this zone, and this slightly darker part is this zone. And the gap here is this part. So what do we observe? We observe a gap here, which is approximately 20 micro arc seconds, or 20 micro arc seconds, sorry. This dark zone is 20, and then there's a peak at 40, this 20 and 20 at 40, and the whole black hole, this black hole is 80 micro arc seconds in diameter. So what am I saying? This part, this 40 or the baseline is 4 times larger than the dark spot here. Okay, so Einstein's prediction was that the photon ring must be here. Okay, but now they've not yet observed the photon ring because the EHT does not have that resolution to see it. But they are saying that general relativity's prediction is within the 68% credibility interval. Why? Because this luminosity profile is not within these blue lines. It's not within these blue lines. So it's not 100. If this whole profile was inside, then we would say general relativity is 100%. So what about quantum gravity? As I said before, this distance of the inner shadow is 4 times less, or the outer one is 4 times bigger than the inner one, and that there's a peak emission at this zone. At this level, the quantum prediction is within 99% credibility interval. Why? Because it's predicted 4 times the dark shape is, this dark shape is 4 times smaller than the outer shape. And that there's a peak of emission at these zones that coincide with the ring for the general relativity prediction. If we look at that 2013 long photo exposure, we will look at it, you'll find exactly like that diagram. There's a D, if you measure this distance, is 4 times less than the outer distance, or this outer is 4 times wider than this, and that there's a peak emission again at that predicted zone. So this zone is a peak of emission according to quantum gravity. But according to general relativity, this is a photon ring. And for the 2022, the latest picture, we can also superimpose the predictions of quantum gravity. You'll find that this outer zone is 4 times larger than this inner shadow. This inner shadow has also been verified by other observations, not only from the EHT, but other 2 observations. You will find that the inner shadow is also been observed to be 26. Now, this yellow circle here is where general relativity assumes that the photon ring is. But in quantum gravity, that's the peak of emission. So far, general relativity had 1 parameter to be verified, but quantum gravity had 3. It had to pass all 3. It has to pass this, the prediction of the inner circle, it has to pass the prediction of the peak of emission, and it has to pass the prediction of the size of the outer circle. So it is 3 times more likely to fail than general relativity, but yet it has succeeded in all 3 levels. Now, we can also look at some other data regarding black holes. This has to do with the LIGO, the gravitational wave detector. In general relativity, it is predicted that when 2 massive black holes are coming to collide, they will collide with an in-spiral speed that is 40% the speed of light. Maximum, in general relativity, the predicted in-spiral speed of black holes is 40% the speed of light. Whereas in quantum gravity, the minimum is supposed to be half the speed of light. So let's look at the data. You'll find that for these gravity wave signals, they could detect that the black holes that collided were moving at half the speed of light. This is 0.53, this is 0.54, this is 54% the speed of light, 53%, 54, 55, 52, 50% the speed of light. As you can see, the quantum gravity predicts a minimum of 50% the speed of light. None of them are below 50 or below 40% the speed of light as predicted by general relativity. So what are we saying here? So far, we can say that quantum gravity is within 99% credibility, confidence level. Now, we are saying that our definition of gravity is the flow of space-time from a region of high vacuum energy density to a region of low energy density. This definition alone affords us to answer the 3 questions. What is gravity? How does it work? And why does it work? That single definition answers all those 3 fundamental questions. So once we understand gravity, we now possess scientific knowledge. Scientific knowledge is a means of production. For example, when people understood how the electromagnetic field works at quantum level, we managed to now have Wi-Fi and all electronic systems that we have. And once we understood how the nuclear forces work at quantum level, we could now manipulate the forces for nuclear energy and other nuclear related productive activity. Now, if we understand how gravity works, it will inevitably lead to technology that can weaken or strengthen it. There are young people in this talk whom I was showing those equations. They will also be interested. They might come quicker with this technology. So even if we manage to reduce gravity by 10% reduction, that will reduce the amount of fuel that airplanes and rockets use and lesser environmental impacts, which means this leads to cheaper resources of outer space. That is, we can access other planets, the asteroid, and mine them instead of mining the Earth. So any society that quickly understands how gravity works and is capable at some level to manipulate it, can access space. And if you can manipulate it at even higher levels, you can even go interstellar. Because our current technology right now of flight is based on our technology moving through space. But as I defined how an apple falls is because of the flow of space. An apple is moving with the flow of space. So if we manage to design technology in which our aircraft flow with space-time, then we become truly interstellar and probably intergalactic, because we will be controlling the flow of space-time. So this is why some of those equations were aimed at the younger researchers, because they might be interested, they might spark some interest in trying to find out how we can reduce the intensity of gravity and how we can manipulate its flow. So with all that, I can say thank you very much. I'm willing to answer any questions.
Okay, just give me a second. So each of you can now unmute yourselves if you want to ask a question. And I shouldn't be running this meeting, so I'm going to stay quiet now that you can unmute yourselves.
Can I ask a question?
Yes, sir.
Stuart, thank you very much. I was completely fascinated by that talk. I had no idea about localities and quantum gravity and the fact that, you know, space can flow. That's entirely novel to me. Thank you so much. I just wondered, does that mean, is this sort of whole idea of the nexus paradigm, is that a new way of looking at gravity and all that? Thank you. Exactly.
You're saying it the right way, because that's the same phenomenon that happened when we moved from Newton to Einstein. We had a different way of looking at gravity, at how it works. So we are now moving from Einstein to quantum. We start seeing a different perspective of how gravity works. It is the flow of space-time from a region of high vacuum energy to a region of low vacuum energy. And this can happen. It's also the cause of the Hubble flow, which astronomers know. Thank you very much. If there's nothing.
Thank you.
Yes.
Oh, thank you very much. Any other questions?
So can I add on that the new perspective of gravity starts from a new thinking about how we see space-time. Instead of seeing it bad points in space, we now start seeing them as localities in space, and localities do not have a zero. So this helps prevent infinities that are currently found in physics, such as standard model of particle physics, as well as black holes, where the gravity becomes infinite. So there's no zero in localities.
Wonderful, wonderful.
Stuart, this was
Any other questions?
This was a very thought-provoking presentation. Thank you very much. I'll be uploading the recording on the Astronomical Society website. Would you mind giving us your email address so that anyone who's listening in or listens to your recording could email you?
Yes, I think Dr. Tsipa has got the email address. He will forward it to you.
All right. If you can forward it here on chat, that would be great.
Again, you want me to type it here on chat?
If you don't mind.
No problem at all.
And while he's typing his email address, let me once again thank everyone who was able to join us. And I must also thank our minister, Dr. Lechola Tebe, the Honorable, who's always supporting us, always present in well, most of the time in our public talks. There is the email. Any other questions? Well, I take it that there are no other questions.
Okay.
So
no
let
problem.
me,
Thank you very much for hosting me.
yeah, let me thank you very much, Stuart Marongwe. Your theory is very, very elegant. And
Thank
you know, we theoretical people, we judge the worthiness of a theory by well, first of all, being able to answer a few things that we can observe, but also in expounding on other things that we didn't even imagine. So your theory is doing exactly that. Thank you very much.
Thank you very much, sir. Thank you, doctor. Thank you.
Thank you, everyone who managed to attend. Hopefully, we'll have another talk end of this month again. Thank you very much.
No, thank you very much. On behalf of the Astronomical Society, I would like to thank everybody who has listened to this talk. I would like to recognize the presence of the minister, and I would also like to thank very heartily the presenter. I would just like to remind that we are a little late for our annual general meeting, and I think it's on a different address. I would encourage members of the society to log in. It won't be a long meeting. Thank you.
Okay. So as I've been hosting this meeting, I will end it now, and I will send the link, because it has been recorded, so that it can be shared with the rest of the society, the video for the recording. Okay.
Thank you.
Okay. You're welcome.